Thank you. Good afternoon. Thank you for having me. I'm Martin Doškář, and this is actually the topic that I covered in my PhD thesis. So today I'd like to take you on our journey from standard periodic unit cell that you might know to something that is beyond, something that is periodical. And my background is in multi-scale modeling and homogenization. And what we typically are interested in is to get some reasonable data for our multi-scale problems. But still, the data should be as small as possible while retaining certain amount of information optimally as much as possible. So, of course, if you are lucky and you are dealing with materials with periodic microstructure, then the solution is readily at your hand because you can take any periodic part of your microstructure and it contains all the data. But because it is really convenient to work with these small periodic unit cells, the same approach is currently being used also for describing microstructures of materials with random geometry of their microstructures. And the reason why we can do that is that typically in the multi-scale simulations, the modeling error that you are causing by assuming some artificial periodicity in your representation is quite okay because there are many other assumptions as a separation of scales, for instance, that this is still okay. But such a representation of your microstructure cannot be used if you want to go to problems where there is no separation of scales, or when you want to use this kind of representation to create some reconstructions of larger specimens. And there are two main problems with that, because once you have your periodic unit cell, you can always get just one realization of your microstructure, nothing more. And there is also some kind of artificial periodicity in that reconstructed sample. So we were looking for an approach that would generalize this problem. And obviously, the thing that you can do is instead of taking one periodic unit cell, you take more of them, right? And the only question is, do you want to be all periodic and all compatible with each other? And we believe this is not the way to go. So we have several modules or tiles, if you wish, and we prescribe some kind of compatibility rules between them. So not everyone can be placed side by side, but there are certain rules how to assemble these small modules, these small tiles into larger specimens. And for that, you can use very simple stochastical algorithm. So let's say you have a set of your microstructure representation in terms of these tiles, and then you want to create a larger sample, maybe like this. So you start and you pick one randomly, and then you look at those that are compatible with this one, you pick randomly again, and so on and so forth. And at each step, you just take some subset of those compatible ones and you pick randomly. But you don't have to pick randomly. You can also have some kind of guided selection. So you prefer tiles that perhaps match some density of a given image. So that's the way how you can introduce some kind of higher order or longer range correlations in your reconstructed samples. So that's a stochastic sequential algorithm with which you can go from the compressed system into certain reconstructions. And in a sense, you can understand this representation as some kind of reduced geometrical model. Because what I really like is the definition of model of material microstructure as a process instead of one realization. So it's a process that allows you to generate individual realizations with given spatial statistics, as you mentioned. So in this sense, our approach is a reduced geometrical model. But of course, the other question is how you design those individual tiles, those individual modules within your set. Because what you want is that when you design them, you want to have guaranteed compatibility. So whatever happens at the red edge of one tile should happen at all the red edges of all the tiles, all the modules. And the second, probably even most important requirement, or more important requirement, is when you assemble those modules together, you should get some kind of continuous microstructure, and that one should be representative of the original material you are trying to compress and then model. And there are several design strategies. We investigated 3 of them, and the first one was really, I would say, a brute force optimization approach, in which you have some, it can be like a particle centers that you move around and you are trying to optimize the 2-point probability function of your representation. and you only have to implement some kind of rules. What happens if the particle moves towards certain edge, whether it pops up in other modules as well, or you can do it also in a voxel way. And it's a very robust approach, but it's really, really slow. It is slow for standard periodic unit cell. And now, as you can imagine, you have multiple cells plus additional rules. So it is really slow. So because we wanted to get something that is much faster, we opted for, let's say, sample-based design. And it was heavily inspired by approaches from computer graphics. And I should also mention that all this tiling idea that comes from the computer graphics community, because they are using this to create natural looking patterns, for example, in images or some kind of visualization. So we also took some kind of inspiration for this sample-based design. And what we did, you just take some samples of your reference microstructure, and then you try to stitch them together with certain overlap. And then there are algorithms that allows you to merge two samples such that there is a seam, but it should be as invisible as possible. And there are algorithms to do that. So you can really take some samples, merge them together, and cut out the future tile. And by definition, by construction, you have the continuity ensured across the edges. Plus, there is the representativeness because you are taking only samples from some reference microstructure. So obviously, the information is already there. You can also add some patching to enrich your compression. There are many ways how to improve it, and I don't want to get into much details here. And as I said, it's a very efficient way because you are just manipulating images. That's quite fast. But the problem with that is that it struggles with complex geometry, such as foams. Typically, it works very fine for particles embedded in a matrix with relatively low volume fraction, because then this tilting algorithm, as we call it, has freedom to really move around the particle so it doesn't disrupt the geometry of the particles. But for example, if you want to compress or model foams with that, then it really struggles. And to get some reasonable design method for foams, we again went to literature and to work by Bernard Sonneau and Thierry Massard from Belgium, and we adopted their level set approach. This is a two-step method that heavily uses on implicit description of particle geometry using level sets. And as I said, it's a two-step method that uses first some particle packing that is accelerated by this level set. So, you know, the trouble with the standard particle packing is if you want to reach higher volumes and you are just picking randomly some centroids of your new particle to be placed, you are quite quickly discarding all the random choices because you have overlap with already placed particles. But when you add this kind of level set information to your domain, then you are just sampling from centroids for which it is ensured that the particle will not overlap with any previously placed one. So it really accelerates random sequential addition or assertion. But also you can take linear combinations of the nearest neighbors, of second nearest neighbors, and third nearest neighbors functions to go from standard particle packing to something that looks like a Voronoi tessellation, this blue one. But this one is more, let's say, complex. It's not standard Voronoi tessellation. It's even more complex. And there is a variant called Laguerre tessellation, which adds weights to the seed points in Voronoi tessellation. But this approach, it adds some local metrics to the seeds. So it's even more complex, and it gives you more freedom in designing the geometry. So this is tessellation-like, so you can get closed foams. But when you take into account also the third nearest neighbor distance, then you can add some kind of plateau-like geometries. In 3D, you have just this material densification around corners, but in 3D, it can produce this open foams, which is rather nice. So as I said, this is a way how to generate very complex geometry. Images are a bit large. So very complex geometries. Now we have the compressed representation, and we can choose whether this is particulate media or some foam-like representation that is just reconstructed from this. The only drawback of this approach is limited statistic control. That's the reason why I was asking about the spatial statistics prior, is that because here everything is based on the particles. So you are just throwing in some particles with given shapes, given ratio, maybe sample from some distribution, but you don't have any direct control over your two-point probability function or any other spatial metrics. So it's a bit of tweaking what are the right parameters to get the desired output. So those are the three methods how to design the compressed representation, as I said. Then you have a set of your tiles, and you can very efficiently, as you can imagine, just putting images side by side, you can generate images, some new realizations of your microstructures. But also, if you have finite element tool that is capable of creating finite element meshes that are topologically and geometrically compatible across the right sides with the same code, you can discretize only the compressed representation and then create finite element meshes for the new realization just by again stacking together different finite element meshes. So that was the first part of our, or that was one of our requirements to create realizations that are random and new. But also the other requirement was about the artificial periodicity, because this is an example of a reference system, some randomly placed equisized disks. And when you compare the two-point probability function, which is correlation of 2 points of the same value being placed at given x1, x2 distance, you see that there's just one peak at the origin, and then it decays quickly, and there's no order in the system. But if you try to reconstruct the same sample with just one periodic unit cell, you can see the periodicity with your bare eye, that's first, but also you can see there's the secondary peaks in the two-point probability function. But if you reconstruct some sample with, say, set of 16 tiles, the secondary peaks are diminished. And of course, the more tiles, the richer your compressed system is, the better this reduction of the spurious periodicity. So that was for the geometry. So we were in a position in which we had tools to generate different microstructures, compress the representation of given microstructure, and then reconstruct individual realizations. And one application for that, we use it to determine RV sizes. It's something we discussed, but that's something I won't talk about today, because the other part of my talk is about numerics, because I enjoy numerics and devising different numerical schemes. And I saw an opportunity here to devise a numerical scheme for these types of problems. To just give you an overview for that, I was dealing with the simplest setup. So it was really just an elliptical equation, scalar one. But the only nasty thing was that we didn't know, or we assumed that it has coefficients that do vary across the domain. But it wasn't allowed to vary totally randomly because we have a tiling concept. So for us, the distribution of coefficients is given by what we call an assembly plan. That's the distribution of the tiles within your domain. And also it depends on the way how the individual tiles look like. So you have this characteristic function, which tells you, for example, tile 3 is here and here. That's where the chi 3 is equal to 1 and it's 0 everywhere else. And then you have distribution AT, that's for the third tile. And then you have this mapping from the global to the local coordinate system. So that's the way how our problem will look like, how the distribution of material coefficients will look like. But we are interested in problems when there are no separate length scales. So it's not a computational homogenization. And we also want to resolve all the local fields, displacement fields, strength fields, stress fields. And we want to exploit the modularity of the long tiles. So, and there are at least 3 possible ways how to approach this problem. One is multi-grid and domain decomposition approaches. That is something that we are exploring nowadays. But our first strategy was use the partition of unity and generalized finite element method. And for that, we assume the split of the solution. So let's say this is a potential solution that we want to efficiently solve. And we split it into a homogeneous part using standard finite element with a finite element discretization that does not resolve any geometrical details. So that's the homogeneous part that would be there if the material was homogeneous. And then we have the fluctuation part that is caused by the presence of heterogeneities in our microstructure. And for this particular part of the solution, we will have some reduced models. We will have some enrichment function that will be pre-computed for each individual part. And the strategy for that part is that we will have some enrichment, some reduced modes that will be a product of the finite element shape functions that we use also for the homogeneous part, and some pre-computed fluctuations, as I said. And then we combine them together using the standard partition of unity ansatz to get some reduced modes. So how do we construct those tile-based fluctuations, those characteristic fluctuations for the tiles? Then this was heavily inspired in computational homogenization. So we impose some macroscopic gradient to each tile, but we then bound them together such that the response is continuous across the matching edges. Because what we could do is take one tile, impose macroscopic gradient, this would be a temperature gradient, and compute the fluctuation for each individual tile. And that would give us some kind of fluctuation field, but that field would probably not be a continuous with other ones. So if we were to assemble them in the same way we assemble the geometry, we would have jump in this fluctuation field. That's something that we don't want. So for that, we ensure the continuity across the matching edges. And we do that by really saying this degree of freedom is the same as this degree of freedom, as the same of this degree of freedom. So we are computing some, let's say, coherent response of the whole set to prescribe deformation gradient or temperature gradient in this case. Plus, you have to pose the uniqueness, but that's that can be easily done by picking either one degree of freedom or just assuming this average condition. And also, we have to ensure the consistency, because otherwise, this sought for fluctuation field would try to compensate for the prescribed deformation gradient. So there are three options how to ensure the consistency, that they are very similar to what you do when you are prescribing boundary conditions in multi-scale simulations. So you can either set the Dirichlet boundary to be 0 at the boundaries of individual tiles, and of course this continuity is satisfied trivially, or you can just impose the 0 gradient tile-wise or set-wise. And it doesn't have to stop at the first gradient. You can also impose some higher gradients and compute that. And this is offline. So you are solving this only once. You have your system, you have your distribution of material within your tile, and that's all you have. And from that, you pre-compute the fluctuations, you store those fluctuations, and then use them for any simulations of large domains, whatever you do. So that's the online solution strategy, that you have two levels of finite element discretization, the coarse one that is there to capture the homogeneous part, and then some assembled fine discretization. I will show you the pictures later. And in this space, that's where all the enrichments were. And we combine them in the partition of unity ansatz, and we pose the problem as reduced order modeling just for the sake of, let's say, convenience, because it's then much easier to do integration, because you don't need any special integration rules, and also simplifies imposing Dirichlet boundary conditions. And the third point I will get to that as well. So let's show it on an example. So we have this L-shaped macroscopic domain. This is the finite element discretization, the coarse one I was talking about. And on the other hand, we have the tile set and the finite element discretization that really resolves all the geometrical details. And for that, we pre-compute the fluctuations, and then we try to plug them in for this particular problem. And we are assuming linear isotropic material and quite a severe contrast in phase properties. So one phase was significantly more conductive than the other. And also please note this dashed line. And this is a cross-section along which I will show a local solution. This is one potential way how the full field solution might look like. So again, there's some overall homogeneous trend, and then there are fluctuations. But as you can see, when you have S, so here I have some parameter S that tells you how many tiles or module I have along this line. So this is for S equals 5. It's already very, very fine microstructure. So the level of detail is quite high. And here you can compare how our approach, what I call ROM, how well it compares to direct numerical simulation, the full field simulation. And when I start with the red one, that's for the coarse discretization that I have here. It's a bit overly stiff in some regions, but once I start refining, uniformly refining that macroscopic discretization, it quickly goes to the right solution. And that's for local errors, and also for the global errors, this epsilon L2 is a relative L2 norm of the difference between the reduced problem and the direct numerical simulation. And as you can see, we are able to achieve quite good results at a fraction of degrees of freedom. And this was average for different, this was 50 microstructure realization. But now, if you have ever worked with reduced order modeling, then you might say, but the reduction is not that great. With standard reduced order modeling, you can go much better. And you are right. But the difference here is that in standard snapshot-based reduced order modeling, you have your macroscopic domain, your loading, and then you start very certain parameters. You compute several snapshots, and from those snapshots, you compute eigenmodes with the highest eigenvalues, and you plug them as your basis function. And your basis functions constructed in this way are very specific for that problem. So you can then just change the loading. So instead of prescribing values here and here, you can prescribe values here and here. And suddenly, your snapshots are totally useless. Well, our approach, we pre-compute something that is purely general. It doesn't know anything about the macroscopic domain. It doesn't know how it looks like. It doesn't know anything about loading. The price that you have to pay is, it needs more degrees of freedom than when it was purely tweaked for this given problem. But then the same performance translates also to different problems, and you don't need to do any retraining. So that's what we believe quite a benefit of it. And the other benefit is that you can easily go to local refinement. So in this L-shaped domain, there is, say, error concentration along this corner, because that's the place where that assumption of uniform gradients along the tiles does not hold. So we can say, okay, I will not use my reduced model in this region. I will switch the reduction off in this region. I will use the full solution in this region, and then I will use the reduced system everywhere. It's really just different projections. It's easily to be implemented. It improves the errors. And that brings me to the very end of my talk. So it had two parts. First was focused more on the geometry. In this part, I was trying to convince you that this one-tile approach or modular approach, microstructural modeling, is just a natural extension of what you know as statistically equivalent periodic unit cell. And there are many names for roughly the same concept. And it allows you to generate almost instantly stochastic realizations of your microstructure with surface periodicity. And it is also a convenient framework for simulations with tunable randomness. And in the second part of my talk, I was showing one numerical scheme that we devised. It combines this tiling formalism, this partition of unity methods, that is capable of generating local fields quite accurately with relatively low number of degrees of freedom, and allows you also the transition to the model. But the story does not end here. We are now working on an extension, because this was more towards modeling existing materials. But now with those meta materials and architecture materials everywhere, and also additive manufacturing everywhere, we are also trying to use this modular concept to design new materials. So we are trying to design modular materials in which you design or you optimize where the modules are placed in your macroscopic domains, and at the same time how the modules should look like. And also we are playing a bit with robots and self-assembly of these modules. So that's the way we are progressing right now. So with that, if you are interested in full details, you can check one of our papers on this topic, you can also follow us on Twitter. And I'd like to thank you for your attention. And if you have any comments, I will do my best to answer them to your satisfaction. Thank you very much.